Propositional theorem proving involves the process of demonstrating the validity of a proposition or theorem within the framework of propositional logic. In artificial intelligence, AI, theorem proving is a crucial component of logical reasoning systems, automated reasoning, and knowledge-based systems. Here's an overview of how theorem proving, inference, and proofs are handled in AI using propositional logic. 1. Logical inference. In AI, logical inference involves deducing new propositions or theorems from existing knowledge using inference rules and logical principles. Propositional logic provides a formal system for making deductions based on the truth values of propositions and the rules of logical implication. Inference rules such as modus ponens, resolution, and truth table enumeration are commonly used to perform logical deductions in propositional logic. 2. Theorem proving. Theorem proving in AI refers to the process of demonstrating the validity of a proposition or theorem using formal logical methods. AI systems employ theorem proving techniques to verify the truth or falsehood of statements, derive new knowledge, or solve logical puzzles. Theorem proving algorithms search for a proof or counterexample to a given proposition by systematically applying inference rules and exploring the space of possible logical deductions. 3. Proof construction. In AI, a proof is a sequence of logical deductions that establishes the validity of a proposition or theorem. Theorem proving algorithms construct proofs by applying inference rules and generating a sequence of logical steps leading from premises to conclusions. Proofs are typically represented as structured objects or formal derivations that can be verified by humans or automated proof checkers. 4. Automated reasoning. Automated reasoning systems in AI use theorem proving techniques to automatically derive new knowledge, solve logical problems, and answer queries. These systems employ algorithms such as resolution, Davis-Putnam-Lodgeman-Loveland, DPLL, and Tableau methods to perform efficient and systematic theorem proving in propositional logic. 5. Applications. Theorem proving and logical inference have numerous applications in AI, including formal verification of software and hardware systems, automated theorem proving in mathematics and logic, planning and problem solving, and expert systems for reasoning and decision making. Overall, theorem proving, inference, and proof construction in propositional logic play a critical role in AI systems, enabling logical reasoning, knowledge representation, and automated reasoning in various domains and applications. Let's consider a simple problem and solve it using propositional logic and theorem proving. Problem. You have 3 friends, Elise, Bob, and Carol. Each of them is either telling the truth, T, or lying, L, about their favorite color. They make the following statements. 1. Elise, my favorite color is blue. 2. Bob, I am telling the truth. 3. Carol, Elise is lying. Based on these statements, determine the favorite color of each friend, blue, red, or green, and whether they are telling the truth or lying. Solution. We can represent the problem using propositional logic, with variables representing the color and truthfulness of each friend's statement. Let \a_b_ represent Elise's favorite color is blue. Let \a_t_ represent Elise is telling the truth. Similarly, define variables for Bob and Carol \b_r, b_t, c_b, c_t \. We can then encode the statements made by each friend using propositional logic. 1. Elise statement \a_b_. 2. Bob's statement \b_t_. 3. Carol's statement \l_t_. Now, We can use inference rules and logical deduction to determine the truth values of these propositions. From Carol's statement, we can infer \L not A underscore T \. Then, from Bob's statement, we know Bob is telling the truth. \B underscore T \. Therefore, Elise is lying. \L not A underscore T \. So her statement \A underscore B \. is false. Thus, her favorite color cannot be blue. We can repeat this process for the other colors, considering the remaining possibilities. If Elise's favorite color is red, \A underscore R \, then Bob and Carol's statements are both true, which leads to a contradiction. If Elise's favorite color is green, \A underscore G \, then Bob and Carol's statements are both true, which also leads to a contradiction. Hence, there is no consistent assignment of colors and truth values that satisfies all statements. This means that the problem has no solution under the given constraints.